Okay everybody, this is the 10-minute tutor and we're back today with another video about free body diagrams and freefall kinematics. So mastering the understanding of free body diagrams is very crucial to learning physics and kinematics properly. When you're given a description of an object, it's very important to know how to draw the proper free body diagram. So what exactly is a free body diagram? So free body diagrams are used to show the relative magnitude and direction of forces. So they show all the forces that are acting on an object in a given situation. And these can be described as vector diagrams since they show the magnitude and direction of the forces. So take for example, we have an object here. I'm just going to label it object A. And it's resting on a table. So I'll just draw a table here. So object A is going to have its weight going down as mg, or simply you can just write g. But going upwards, there's going to be a force called Fn, or the normal force, which is the force of the table pushing up at the object. Meanwhile, mg is the object pushing back at the table. So this is just a simple vector diagram. As you can see, we have our vector arrows here showing the direction and the magnitude associated with it. So the size of the arrows reflect the magnitude of the force, and the direction of the arrows show which way the force is actually acting. And sometimes there's not always 4 or even 3 forces acting on an object, especially in freefall. If you have an object in freefall going downwards, say it just fell off a cliff here, and you have a rock that's falling downwards, really the only force acting on a rock, as long as there's no wind or any type of resistance in a perfect world, is actually just the gravity. So there's only one force in this situation. And if you guys are confused about the different types of forces that I'm talking about, such as the normal force or gravity or even vectors, be sure to check out our previous videos. We've covered vectors, we've covered all the different types of forces. So that'll just sum it up if you guys are confused and want a little bit of extra help. Okay, so let's see. So when you're given a description of an object, it's very important to do 3 things. So the first thing you want to do is use your understanding of the types of forces to identify which forces are present. So your first step with free body diagrams is to identify the forces. Identify forces. Your second step is going to be to determine the direction of each force. Determine the direction of each force. And then your final thing that you want to do to draw a good free body diagram is to draw a box. Draw a box, and then you want to add arrows for each force. Okay, so using the 3 steps that we just talked about to draw the proper free body diagram, we're going to go over 3 problems now and see if we can apply that. So a TV remote is resting on a table. So you have a table here, and then you have your TV remote right here. So the TV remote is resting on a table. Diagram all the forces in an appropriate free fall body diagram. So to make this situation a free fall body diagram, we start off with a box, a simple box. And then now, when we're looking at the TV remote, we're really just looking at this piece right here. So starting from the center point, we know that obviously the remote has a weight to it. So the weight is going downwards as mg. And there's also another force. Since the TV remote is resting on the table, there's a force of the table pushing up at the TV remote. And this would be the normal force, which we talked about in a previous video on forces as the normal force. So we have the mg going down and the Fn going up. They're in equilibrium, so there's no net movement, which is why the object is resting. Another example, so we have a chandelier which is hanging from the ceiling by 2 cables. So we have a ceiling here, and here's one cable, here's another cable, and there's a chandelier right here, hanging off the ceiling. So now we want to diagram the free body diagram. So what we do is we draw the box first, and then we want to understand what types of forces are present. So we know that since we're talking about cables, that means there must be a force of tension present. And since something's hanging, there's definitely going to be gravity present. So we have force of tension and we have gravity. And since there's two cables, there's actually two FTs here. So now to just draw it down here, just to make it a little bit more clear, you're going to have a free body diagram of an FT, one FT going up for one of the cables, another FT going up for the other cable. These are really supposed to be the same length. I just tried my best. And then you're going to have the weight going down as mg. So that's how we draw the body diagram. You know that we have cables, so we're talking about force of tension, and since something's hanging, obviously the weight is playing a role. There's no normal force since nothing's resting on, there's nothing to be pushed, there's nothing pushing the chandelier back up. Okay, and last problem, considering friction, a rightward force is applied to a box to make it move across the table. So you have a table here, and you have a box on the table, and there's a rightward force acting on the box. So now when we look at this, we have to see what kind of forces we have. So since there's a rightward force, that means we have an FA for applied force. Applied force. We're also going to have mg, since it's acting downwards. Well, since there's an object resting on something, so it has its weight. There's also an Fn, since the table is going to be pushing back up at the box. And we also have the force of friction, or Fk, because we said to consider friction. So now to draw this free body diagram, we're going to have friction. So it's moving right, so we're going to have friction acting in the opposite direction. There's going to be an applied force going in the right direction. You're going to have your Fg for F gravity, or you can just write mg heading downwards, and then you have your normal force going up. The forces that you're going to have in this situation. Okay, so now I just want to get into the basics of freefall. I'm going to talk more about the equations in the next video, but for now I just want to lay down a couple of important characteristics to know. So freefall is just, if you want to even call it, it's just a fancy term for an object falling under the sole influence of gravity. So there's a couple important characteristics to know that apply to nearly all freefall problems. So the first one is, there's four we're going to be talking about. So unless thrown, the object has an initial velocity, or VI, for initial velocity, of 0. So unless it's thrown, the object will have an initial velocity of 0. So if it's, unless it's like projected in some way. So a second characteristic to talk about is that an object in freefall has an acceleration of 9.8 meters per second. So A for acceleration in freefall, abbreviated as FF, equals 9.8 meters per second squared. And I'm writing negative because when we're talking about acceleration, it's a vector quantity, which we're going to be talking about more. So since it's a vector quantity, we have to state the direction, and the negative just indicates that it's free falling downwards, so it's heading downwards. So that's another important characteristic to know, that an object in free fall has an acceleration of 9.8 meters per second squared. So another thing to know is that if an object is projected upwards, it will slow as it rises upwards, and then when it reaches the top of the trajectory, the velocity is 0. So just to demonstrate what I'm saying, if an object is thrown upwards in a trajectory like this, a ball, and then it's coming back down, it will go up and up and up, and it will slow as it gets up, and then it will drop back down. So this is only when it's projected. So when an object is actually thrown upwards in this direction, it will slow as it rises, but then when it reaches the top right here, this is going to be the VF, or the final velocity at the top of the trajectory, is going to equal 0 meters per second, because it actually comes to a stop when the object gets to the very top. So that's something very important to know if an object is projected off the ground. A fourth thing to know is that if a ball or object is projected upwards in a perfect vertical direction, the velocity it is projected, or the VI, is equal in magnitude but opposite in direction to the velocity at the same height. So if you throw a ball upwards, just picture this going upwards, so it's going up, and then it just comes right back down. So at this point right here, just pick any point, the velocity here, say it's 10 meters per second plus, because it's going upwards. But then, as the object rises, and then it comes back down, at this point, on its way back down, we could say that the final velocity is the same. It's 10 meters per second in the negative direction. So that's something important to know, is that objects that are projected upwards in a perfectly vertical direction, the velocity, or the VI, is equal in magnitude but opposite in direction to the velocity at the same height.